So, good afternoon everyone. You are welcome for the afternoon session for Gyan program on Aeroelasticity and Unsteady Aerodynamics in Turbomachinery. In the morning session, we have discussed about say aerodynamics of axial flow compressor. We have discussed instabilities, that's what is arising in axial flow compressor. So, this sessions basically we will be discussing about say fundamentals of turbines aerodynamic and flow instabilities, that's what is happening inside the turbine. So, if we look at here, this is what is a triangle. Yesterday Professor Maiti has discussed of, today morning also we have discussed a little. Now, in this triangle, if you consider when we are talking in terms of turbine, then we will be having temperature effect that will be coming into the picture. So, along with this triangle, you will be having fourth force also, that is what we can say thermal force that will be coming into the picture, and that is what is playing important role when we are talking in terms of say turbines. Now, after completion of these lectures, the participants will try to understand, like they will be having those who are not having the exposure as we have discussed of turbomachinery, they will understand the basics of this axial flow turbine. Then we will be discussing about the three-dimensional flow field, that is what is creating inherent say unsteady flow field, that we will be discussing, and operational instability in the turbines, that is what we will be covering today. Now, in overall, once you will go through this lecture, you will be having basic background in terms of understanding the flow unsteadiness and aeroelasticity, that is what is happening inside your axial flow turbine, which will be covered by Professor Watanabe from tomorrow. Now, let us try to understand, this is what is a representation of the engine. If we look at here, in the morning we have discussed about this particular region, what we say as axial flow compressor. So, we are having axial flow fan, then we are having IP compressor, then we are having HP compressor. Similarly, after combustion chamber we will be having HP turbine, we will be having LP turbine. Now, if we look at in terms of say HP turbine, it is not for generation of HP, but its operating pressure is high, and that is the reason why this particular section, that is what has been defined as HP turbine. This HP turbine that will be rotating at very high speed, that is what is the requirement of my HP compressor, because in order to have very high thrust to be generated, we need to rotate or we need to have our compression to be slightly higher. In order to have that higher pressure ratio, you need to have the rotor to be rotated at very high speed, and that is what is been accommodated by few stages of HP. Here if you look at, we are having two stages of HP turbine. So, in construction if we look at carefully, after combustion chamber we will be having nozzle like this, that is what is known as nozzle guide vane. What it will be doing? It will be guiding my flue gases towards the rotor, and that rotor that will be subjected to expansion, and that is what is generating my power. That power, that is what is used to rotate our compressor. Now, in terms of flow passage, as we have discussed in the morning, what is our observation here? Since my temperature is higher, so my density that will be say lower, and that is the reason in order to have your continuity to satisfied, we will be having our area, that is what is continuously increasing. So, you will be having divergent shape of passage. Now, here in this case if you look at my HP turbine blades, they are slightly of low height. If we would like to have look at, this is what is a nozzle. We are talking of HP turbine nozzle. So, this is what is the size we can say, it is around say 2.5 centimeter to 3 centimeter, it may be even lower than that. Okay. Now, if we look at here in this case, this particular region where you will be having your flue gases, that is what is having very high temperature. So, when this high temperature that will be striking on the nozzle, there may be possibility or it is for sure your nozzle vane will get melt. So, now in order to avoid that situation, it need to have special kind of cooling that need to be provided. if you look at here, this is what is one of the nozzle. In that nozzle, from trailing side, this cooling, that's what is provided, and that cooling hole, that will be starting from the base. If you look at here, from base, my gas, that's what is, or my air, compressed air from HP compressor, that will be supplied here. Now you need to understand, we need to have the flow along with my flue gas. That's the reason why high pressure air, that's what is required for the cooling purpose. Now moving downward side, if you look at my blades, they are of high aspect ratio, or they are the taller blades. So if you will look at here, this is what is my LP turbine blade. Now for this LP turbine, if you look at what is the speciality here, if we look at the aspect ratio, that's what is different. And if you compare in other sense, my chord, what we say, axial chord, that's what is the distance from leading edge to trailing edge, that is also less. And if we consider for say HP configuration, we will be having chord that is slightly larger, okay, and that aspect ratio will be in the range of 1. Now there is a whole discussion in terms of having say number of stages. When we are talking in terms of say aircraft engine, application to say military engine, where weight is our one of the constraint and compactness is a basic requirement. Under that condition, what is happening, like your number of stages for HP and number of stages of LP, that will be lower. You want that to be lower. Now here in this case, when we are talking in terms of say commercial aircraft, for that you need to rotate the fan, that is what is rotating at the lower speed, and that is what is been connected on LP spool. Okay. So here in this case, as our target for say commercial aircraft is to have very good fuel efficiency in terms of lower specific fuel consumption. And if we consider, it says more the number of stages of your turbine, higher will be the efficiency. That's what we are defining in thermodynamics as polytropic efficiency and isentropic efficiency. So more the number of stages, more will be the efficiency in that sense, and that efficiency will be in the range of 90 to 92%. Now when we are talking in terms of application, say especially for military purpose, we can say we cannot have this many stages, because we have constraint with our size as well as weight. Now this is what is the Trent 500 engine. If you look at, this is what is my HP nozzle, that's what is operating at 1600 degrees centigrade. Now if you look at, this is what is powering our Airbus 340, 500 and 600, and that's what is generating 36.5 megawatt power during the takeoff. Okay. Now that is what is equivalent to 25 split fire aircraft or Griffin engines, like that's what is having say 2000 HP power. That is what is having say 700 total, you are having say 70 blades, that's what is being placed in my HP. So each, that's what is generating 700 HP power, that is equivalent to your one F1 car engine. You can understand what load, what thermal load we are talking of. Now at the same temperature, maybe if you are putting for say our flask, then it will get melt under that condition within 0.5 seconds. You can understand what temperature we are talking of. Now here in this case, HP turbine blade, that will be subjected to say gravitational load of 60,000 G during the takeoff condition. So this is what is called like real engineering in that sense. Now let's try to understand what we have discussed in terms of our velocity triangle. So now here if you look at, this is what is my stator blade and here is my rotor blade. Now we need to understand what is our requirement. We would like to extract the work from our rotor. Now in order to extract the work, you need to take the benefit of your lift force. So in this condition, if you look at my rotational direction, that will be from my suction side towards the pressure side. That's what we have considered reverse in the case of our turbine. Okay. Now, here my flow that will be entering here. So, this is what we are talking in terms of say our compressor blade. Okay. So, here we are having our movement of my rotor that will be from suction side to the pressure side, as we are utilizing our force or say our lift force for the compression work. Okay. And here we have observed this is what is my absolute velocity, this is my rotational velocity, and that is what is resulting into our relative velocity component. So, if you look at this is what is representing my absolute velocity streamlines, here this is what is representing my relative velocity streamlines. Now, what is happening? My flow that will be entering with relative velocity V2 to the rotor, and it will be coming out at the exit with some velocity say V3. And we have discussed in the morning, say when we are having this relative velocity, that is what is decreasing, that is what is the indication of my diffusion work. Okay. Here my absolute velocity is increasing and relative velocity, that is what is decreasing. Now, let us come towards say our turbine side. So, here we will be having say we are having our stator and rotor combination. Okay. Now, from stator my flow that will be coming out with some absolute velocity C2. Okay. Now, what is our purpose? We want to have extraction of our work. In order to have that extraction of our work, we need to rotate our blade from pressure side towards the suction side. We are utilizing our lift force to extract the work, and that is the reason why this is what is my rotational direction, and it will give me my relative velocity V2. What is happening? Once it is passing through my rotor, it will be coming out with relative velocity V3. That is nothing but my relative velocity we are getting higher. If we move back, this is what is the comparison sort of thing for your compressor as well as turbine. So, for turbine what we are getting, we will be having lower velocity, lower absolute velocity with which my flow that will be coming out. Okay. Now, here if you look at carefully what is happening on the upper region, like this area, and if I move towards the downward side or trailing edge side, my area that is what is decreasing. If we compare for our compressor, what is our observation? My inlet area is lower and my outlet area is higher. That is what we say in terms of say it is acting like a diffuser. Now, here in this case, this is what is acting like a nozzle. This is what is giving you say your conversing passage. Okay. Now, let us try to understand this velocity triangle. As we have discussed, this is what is my nozzle, that is what is having say my absolute velocity C1 with which my flow is entering, that will be coming out from small area AC2 with absolute velocity C2, and my flow that will be entering with relative velocity with area of AV2 and AV3. So, if we will be putting our velocity triangle, this is what is our velocity triangle. Here let me explain. The thing is, the angle what we are measuring, these angles are measured along the axial direction. So, conventionally people they have started with say turbines with steam turbine. So, for steam turbine they were having their measurement of angle with say tangential direction. Okay. And many books what you are referring or literature you are referring, they are still following the same concept as say steam turbine concept. Okay. Here we are talking in terms of angle like this. This is what is my section if I say at some mid section. So, you can understand here again, this is what is my mid section where I will be having this velocity triangle. Now, what is happening? We have our nozzle, that is what is moving from, or that is what is having span from hub to shroud. Same way we are having rotor, that is what is having span from hub to shroud. So, along the span we will be having variation in radius. So, when your radius that is what is varying, your peripheral speed is varying. So, component of peripheral speed u that is what is varying. When your v is say u is varying, your axial velocity is constant, your blade angle that will be varying all the way from hub to shroud. Okay. And if you understand, like here also, truly speaking, in sense of aerodynamics, what people they understand aerofoil is not straightway applicable here. Okay. Here each aerofoil, it has to do some work, and that work, what we are saying, we are extracting the work in terms of turbine. Okay. Now let us try to understand what we have discussed in the morning for say axial flow compressor. Similarly, we can write down the Euler's equation for the turbine. Here this is what is getting added up, and if we consider, we are having two kind of work here also. One, that is what we say as aerodynamic work, that is what is represented in terms of velocity components and flow angles. Similarly, when we are talking in terms of thermodynamic work, this is nothing but my expansion work. My T01, that is what is my turbine inlet temperature, and T03, that is what is my exit temperature. Logically, if we say this, both the work need to be same. Now this is what we are talking in terms of say my TS diagram for the turbine. Now state 1, that is what is representing my flow, that is what is entering at the stator. Now when it is entering with the stator, it will be having some absolute velocity, and that is what is giving me my T01. That is what is my temperature T01 and state 01. What is happening? That is what is entering inside my stator. Now stator, it is not doing any kind of work. So we can consider that process as adiabatic process, and that is the reason why we are assuming our T01 and T302, that is what is same. But it is interesting to observe my total pressure, that is what is reducing. So based on my P02 location, if I accommodate C2 square by 2, just try to understand, we are talking about C1 and C2. What is happening? My C2 is larger than that of my C1. That is what is representing my expansion work or the acceleration work. So this is what is my state 2. Now for this state 2, what is happening? That is what is entering inside my rotor. Now when it is entering inside my rotor, that is what is been spatially been represented in terms of relative velocity component. So here this is what is represented as P02 relative and P03 relative. And for rotor, we can say our relative temperature, relative stagnation temperature, that is what is remaining constant along my blade. Okay. And this is what is the location from where my flow that will be coming out, and that is what is. So conventionally design, if we are talking of, people used to prefer the design in which my C1 and C3 that will be coming same. This is what is about the thermodynamics, what we are talking of axial flow turbine. Now let us come to the next parameter what we are talking, that is what is my flow coefficient. Now what is our assumption for axial flow turbomachinery? We are assuming our axial velocity to be constant. Now conventionally what we understand, my flow path need to be parallel one, but what is our observation? Along my downside movement with say expansion work, my passage, that is what is increasing. Okay. So conventionally what people say, like flow coefficient that need to be in the range of 0.4 to 0.6. What is the importance of that? Very soon we will see. Now let us try to understand in terms of say flow coefficient. Suppose say I am having higher flow coefficient. What it means? Higher the flow coefficient, higher will be your velocity, or lower will be your peripheral speed. Or you can say here in this case, higher will be my rotational speed, okay, or the diameter. So what is happening? If I am increasing my flow coefficient, that means I am increasing my CA, absolute say axial velocity component, my Mach number that will be increasing, that will reduce my flow angles and turning both for rotor and stator. What is happening? I will be having smaller annulus height. Just try to correlate in terms of diameter. Okay. Now, that will increase the chord length or say number of blades in order to achieve the work. It will increase the cost. You will be having your aspect ratio to be lower, and your secondary losses, what we will be discussing soon, that will be increasing. So, smaller and lighter blade that will subjected to stress, that also will be reduced. Now, what is happening, my hub diameter will be increasing. So, leakage loss also will be increasing with increasing in the area of the seal, because my hub diameter, that is what is slightly larger. My tip gap, what we say height, that is what is subjected to my tip clearance losses. What it says, mainly when we are talking in terms of military application, where our criteria is size and weight with efficiency and cost, that is what is not a major criteria. Under that condition, it is preferred to move with high flow coefficient design. Okay. Now, when we are talking in terms of say reduced flow coefficient, the reverse will happen. What will happen? My Mach number, that will be reducing, my flow angle, that will be increasing, I will be having larger annulus height, that will be reducing the chord and number of blades, that will reduce the cost, aspect ratio also will be increasing. So, my losses will be lower, my hub diameter also will be reducing, and that is the reason why losses they are reducing. Mainly when we are talking in terms of commercial or civil aircraft, where the specific fuel consumption, that is what is of major criteria, and efficiency is a criteria. Under that condition, low flow coefficient design, that is what is being preferred. Okay. Now, let us try to understand what exactly the meaning is, because since we are talking in terms of say gas turbine engines, that is what is applicable for both your aircraft engine as well as for land based power plants. So, this is what is representing my psi versus phi, and these are my efficiency lines, and these are my nozzle angles. If you look at, this is what is my blade angle. Now, I have located three different points, point A, point B and point C. Suppose say if I am talking about point A, what is our observation? I am having my lower value of phi in the range. Same way I will be having psi to be lower. Under that condition, what will happen? You will be having say larger area, what we have discussed for the same mass flow rate. So, industrial turbines where you are having size and weight not as a criteria, only specific fuel consumption as our criteria, then this kind of flow coefficient we are selecting. Now, here if you look at, for that point my efficiency will be in the range of 94, 96. Similarly, if I am moving towards a point B, what is happening? I will be having my flow coefficient to be in the range of say 0.6 and my loading coefficient, that is what is say 2. Now, under that condition I will be having minimum flow area. The size and weight, they are of little concern, and say lower specific fuel consumption, that is what is the criteria, then people they are preferring to have this kind of selection for phi and psi. Now, let us move towards say point C. If we look at, we are having higher range of flow coefficient, we are having higher range of loading. What is happening under that condition? What we say, our annulus area, that will be lower. What it means, like especially when we are talking in terms of size, what we say compactness and weight are the criteria. Under that condition, this design or this selection of criteria is important. So, mainly for aircraft engine, it says they are selecting the loading coefficient in the range of 3 to 5 and flow coefficient in the range of 0.8 to 1. Okay. Now, here if you look at, this is what is my velocity triangle. Now, for aircraft engine, suppose I am talking about the later stages, say LP turbine, my flow that will be coming out at certain angle, suppose say it is coming out some angle say alpha 3, that is nothing but my flow angularity. Now, that angular flow when it is entering downside, say in tail or nozzle, that is what is subjected to loss. Okay. So, in order to avoid such kind of situation, we need to have our flow angle, exit flow angle, that need to be lower, and that is what is being preferred. So, it says in literature openly saying like 50% reaction design, that is what is a preferred design when we are talking in terms of such applications. Now, this is what is known as Smith chart, and this is talking about whole what you need to do in terms of selection. So, if you consider this is what is my stage factor or say flow coefficient, and this is what is my stage loading factor. So, if we consider here, so what Smith has done, he has collected all the data experimentally, those which were available, and he has plotted for flow coefficient and stage loading coefficient, and based on that what efficiencies they have received, that is what they have plotted. Now, here it is interesting, like suppose say I am selecting what is my criteria, my loading coefficient I am expecting 1, I can have two different values. I can select my phi as 0.6, I can select my phi as 1.2 also. What is your observation for both of this? Here if you look at in terms when I am moving towards say lower side, as we have discussed in terms of low flow coefficient selection, my turning angle will be larger. So, here my turning angle is larger compared to this. At the same time, if you look at the shape of my aerofoil, they are different. Now, let us move towards a higher side, because when we are talking in terms of application of these blades for say aircraft engine, we would like to have less number of stages, means per stage my loading need to be higher. What I need to do, I will be selecting larger load and higher flow coefficient. So, this is what is my configuration. Okay. At the same time, if I am talking in terms of say low, you can clearly see like my turning, what we say flow turning angle, that is what is larger when I am selecting lower limits. Okay. At the same time, what is happening, my degree of reaction, that will be changing. Very soon we will be discussing this degree of reaction, that is what is very important when we are talking in terms of say turbine. Morning we have discussed about say axial flow compressor, in that also we have defined the degree of reaction, that is what is not perfectly fitting in that direction, but this is what has been dedicatedly been defined in terms of say degree of reaction for turbine. Now, this is what is the data, that is what is collected by say MTU engines. They have collected the data, what they say is like what need to be the range. If we look at here, they have selected this data for HP turbine, for geared LP turbine, direct drive LP turbine. Okay. So, this is what is my efficiency line. So, most of the cases if you look at when I am talking in terms of HP, that is what is defined with lower flow coefficient and comparatively higher loading. Similarly, if I am talking in terms of say LP turbine, that is what is with slightly high flow coefficient. Okay. So, now you need to understand what we are talking in terms of turning of my blade or turning angle here. This is what you need to understand. Okay. Because at this moment the curved blade looks very nice, but when it is put on say rig for testing, you will understand it is having lot of difficulties. Okay. Now, so let us try to understand here, as I say my degree of reaction, that is what we are defining in terms of say turbine. We can have say degree of reaction to be 0, we can have degree of reaction 0.5, degree of reaction say 100% or say 1. What is happening if I am considering my degree of reaction to be 0? What it means, I will not be having any enthalpy rise dedicatedly in terms of say rotor. So, if you look at my expansion, that is what is happening only in stator, and in my rotor there is no pressure, a change of pressure. So, my expansion is happening only in the stator. Now, when I am talking in terms of 50% reaction, what is happening? I will be having my expansion both in rotor and stator. Now, let us move towards say 100% reaction. What is our observation? Here in this case, slight change of my pressure, that is what is happening inside the stator, and I will be having say my expansion, that is what is happening mostly in my rotor part. Okay. So, the thing is hold your acceleration, that is what is happening only in the rotor and producing say that is what is increasing the losses. So, now this is what is talking in terms of say overall idea. This degree of reaction terminology, that is what is related with the efficient say enthalpy, that is what we say thermodynamic term. People they have defined that in terms of flow angles. Okay. Now, if you try to understand what is happening near the hub and what is happening near the tip, that is what will give me my variation of degree of reaction. I mean to say my degree of reaction, it depends. My degree of reaction that will be varying all the way from hub to tip. There are few designs in which they are dedicatedly putting degree of reaction constant. So, degree of reaction say 50% throughout the span. Okay. So, now if you look at, you might have observed like this is what is my blade, that is what is say low cambered blade, and here if I look at, this is what is highly cambered blade. Both of them they are in say generating the lift. Now, what is our observation? Suppose say if I am talking about this blade, now my inlet pressure is say P1, my outlet pressure is say P2. If I am talking of say my outlet pressure is higher, what will happen? Now, when my outlet pressure is higher, then I will be having my flow that will be accelerating, and then after it will get decelerated here. Okay. Now, if you look at, we have discussed in the morning, mostly for axial flow compressor our blades are low cambered aerofoils. Okay. Because my delta beta is limited. Why delta beta is limited? Because we are having flow separation problem, because it is working under adverse pressure gradient. Now, let us try to understand this. If you look at, this is what is highly cambered aerofoil. Suppose say if I am applying here say pressure P1 and pressure P2. Suppose say if I will be having higher pressure at the outlet side, what will happen? Because of this turning, my flow will get separated. So, I cannot have this highly twisted blade. Now, when I am talking in terms of say turbine, what is happening? We are doing expansion work. That means my exit pressure is lower. We can say we are in favorable pressure gradient. In compressor, we are working under adverse pressure gradient. Here, we are working under favorable pressure gradient. Under favorable pressure gradient, the chances for the flow separation are less, and that is the reason why this turbine, that is what is having the highly cambered, okay, or high cambered, that is what is been provided for the turbine. Okay. Now, if you look at what we have discussed in terms of say our angle here beta 3, this beta 2 plus beta 3, my delta beta that will be larger. So, larger the angle, more will be the work done, or more will be the work extracted. Okay. Now, let us try to understand what we know in terms of say our CP distribution. In the morning we have discussed for axial flow compressor, my CP plot, that is what is representing my amount of compression work done. Okay. Similarly, for turbine also we can say this curve, area under this curve, that is what is representing my work that will be generated by the turbine. Okay. Now, here in this case we are having leading edge and trailing edge. Now, passage, if you look at here, this is what is say, I say this region, that is what is defined as a throat region, that is what is having minimum area. Okay. Now, what is happening? Suppose say if I am plotting, it is a reverse plot. Okay. For turbine people, they are putting that in a reverse way. So, this downside, that is what is representing my pressure surface, and upside, that is what is representing my suction surface. What is happening on my suction surface? If I will be talking of all the way up to maximum camber, this location, I will be having my acceleration of flow, and then after my flow that will be following this path, it says like it is moving downside. Okay. Similarly, what is happening on the pressure side, I will be having my acceleration of flow, and maybe that is what is having slightly in terms of say acceleration. Okay. Now, when we are talking, this is what is representing my velocity. Now, the flow over this turbine aerofoil, that is what is complex in sense. For say compressor also it was complex, but here if you look at what is happening, I will be having my laminar flow, that is what is happening near my leading edge, and then after it is accelerating flow, I will be having transition that will be happening somewhere here, and after transition I will be having my turbulent flow. Okay. Similarly, downside also I will be having laminar flow and you will be having transition flow, that is what is happening. Now, since this is what is the area, that area is lower, my velocity is increasing. What it means, I will be having choking condition, or what we need to understand, we will be having say acceleration of flow, that is what will generate my shock structure downside. Okay. So, because of shock, suppose if I consider this is what is a shock, that is what is being placed here, what will happen, upside I will be having low pressure, downside I will be having high pressure. Now, what is happening, my flow now that will be working under adverse pressure gradient. So, people say the chances for the flow separation on turbine blade, it is there are no chances, it is less. But when we are talking in terms of say transsonic flow, that is what is happening in the passage, we will be having chances for the flow separation to occur near this trailing edge. Okay. Now, let us try to understand the terminology, because this is what is very important in terms of understanding the aerodynamics. Now, here this particular region, that is what is known as say wedge angle. This wedge angle is nothing but when I am drawing my tangent from at the leading edge from my suction surface and pressure surface, that is what is generating my wedge angle. So, if you consider larger will be my wedge angle, what will happen in terms of my flow physics? More will be my flow acceleration, that is what is happening. Okay. Now, here if you consider I will be having more acceleration, that will be happening. If I say my wedge angle to be lower, what will happen? I will be having my acceleration up to certain limit. Okay. So, now the situation is on the blade surface, my acceleration that will be attained up to certain limit, then I will be having my transition flow, that is what is happening, and later on I will be having my turbulent flow. Okay. And under turbulent flow, after some distance, as we have discussed, there may be chances for the flow to get separated. Okay. One more thing what you need to understand here is, suppose say my flow is entering here. Now, that is what is leaving from this region. When it is leaving, what is happening? Suppose say because of this as a solid body, you will be having growth of boundary layer. In case of change of my flow pattern or the stagnation point, I will be having larger wake that will be coming out from the exit. So, larger will be the angle, larger will be the wake. That way you need to understand. Suppose say this is what is representing say two different sections, say section A and section B. Let us try to understand. Suppose say if I am talking about the section B, that is what is towards the tip. What is happening? My stagnation point, that is what is placed slightly towards my pressure surface. So, what it will do? I will be having, suppose say if I am talking about say my pressure surface here, this is what is my velocity what we are talking of. So, my velocity, that is what is decreasing here. Okay. And then after I will be having my increase of velocity. So, my velocity that will be increasing relative velocity what we are talking of. Now, similarly my flow will try to turn through this leading edge. So, I will be having my recirculation zone that will be formed here, and that recirculation zone, if you look at, if you compare these two profiles, you can easily understand my amount of work what we are expecting or amount of pressure rise or what we say in terms of Cp, that is what is different for both the sections. Okay. Now, if we consider say section A, what is our observation? My stagnation point, that is what is placed here. So, I will be having my smooth flow, that is what is moving towards the leading edge and trailing edge, and that is what is giving me this kind of distribution. Okay. So, next term, that is what we have discussed in case of say compressor, what we have discussed when we are taking the sign convention, if we will be having flow that will be incidenting on say pressure side, we are defining as positive incidence. Okay. Similarly, for this case also we are talking in terms of when my flow, that is what is impinging on my suction surface, we are talking that as a negative angle. Okay. So, here if you look at, this is what is having say positive incidence angle. Here if I am talking in terms of rotor, that is what is having negative incidence angle. Now, next term, that is what is say in terms of leading edge thickness. So, this is what is my maximum thickness, that is what is occurring. What will happen now, because of this maximum thickness, as we have seen, we will be having our acceleration of flow up to certain distance, and then after my flow that will be following this path. Still it is having acceleration, but on the downside after this throat we will be having say my deceleration of the flow. Okay. So, larger will be the thickness, more will be the acceleration you will be getting near the leading edge. So, if we are talking in terms of say Cp distribution here, suppose say if I am talking about this is what is my maximum thickness, you can understand what we are talking in terms of my suction surface. Okay. So, this is what is representing that incidence angle what we are talking of. So, suppose say if I will be having positive incidence angle, I will be having my acceleration of flow up to certain distance, and then I will be having transition. If I will be having negative incidence angle, then I will be having flow, that is what is moving, or what we say in terms of we will be having deceleration of flow up to certain distance. Okay. And this is what is people they have defined in terms of say induced incidence angle, that is what is experimentally they have found. What they say, based on this inlet flow angle, you can choose say incidence angle. Now, there are types of bleeding what we have discussed in terms of say degree of reaction. So, if we consider, as I told, one of the parameter, that is what we are defining as a profile loss. Profile loss, that is what is nothing but that is what is because of my the flow, that is what is behaving on my suction surface and pressure surface. If you consider here for my reaction blade, I will be having my profile loss to be lower. At the same time, when I am talking in terms of say impulse bleeding, I will be having my profile loss to be large. Okay. And this is what is representing so impulse kind of bleeding, and that is the reason why earlier we have seen the impulse kind of blade, that is what is generating lot of losses, and that is the reason why conventionally speaking, when we are talking in terms of say gas turbines, people they are avoiding to have impulse kind of design, or by force when we are making the blade, somewhere in some section you will be having say your reaction blading, and somewhere in region you will be having impulse. Pure impulse, that is what is not preferred, because it is having say losses. Now, let us try to understand the shape of different leading edge. Okay. Now, if you look at here, there is a thick leading edge, you are having thin leading edge, you are having say elliptical leading edge. Okay. Now, let us try to understand in terms of what we say the loss coefficient versus my incidence angle. So, when we are talking in terms of say this plot, particularly when we are talking in terms of say configuration B and C, if I am having low incidence angle, then it says I will be having lower losses. Okay. So, when we are talking in terms of losses to be lower and I need to have my flow, that is what is like I can accommodate, that is what is been cared by having say thin leading edge or elliptical leading edge. Now, when we are talking in terms of thick leading edge, you can understand my losses, that is what is going to increase. Okay. But at higher incidence angle on both extremes, if you consider comparatively low, your losses are less. Now, let us try to understand what exactly it means. Suppose say I am talking about say HP nozzle. what is happening, my flow that will be coming out from the combustor and it will be striking on my nozzle. Now, when it is striking on the nozzle, that is what is striking at very high temperature. So, what you need to do? You need to have cooling of that. So, in order to have your cooling mechanism, you are forced to have thick leading edge. When we are talking in terms of say later stages, say HP, LP, what is happening? My operating temperature is not that much. So, that will cross my melting temperature of the blade. Under that condition, we will be having say thin leading edge and elliptical leading edge. Very soon we will be look at like my flow that will be with what will be coming out from the nozzle, that may be transonic flow or say supersonic flow, and that transonic and supersonic flow, that is what is generating the shock structure. So, if I will be having say thick leading edge, I will be having standing of say bow shock. So, you may need to have this kind of blading. Now, this is what is one of the representation, what in terms of modification what is happening. Here if you look at, this is what is the leading edge initially they have done. Then after they have removed some portion here. Now, you can understand slightly removal of your leading edge surface, what it is doing here. Just try to understand, say this is what is my CP distribution. What was happening here in this case, I was having my acceleration and then after its deceleration, and again I will be having my acceleration. Now, in the case when they are removing this surface, I will be having small acceleration and I will be having very smooth deceleration. That is what is happening in that sense. Okay. Next, that is what we are defining in terms of say uncovered turning angle. What is that? If you look at here, this is what is known as a uncovered turning angle. When we are drawing tangent from the throat and when we are drawing tangent from my trailing edge, it will be matching somewhere and it is having say this angle. That angle we are defining as uncovered turning angle. Now, conventionally people they were not putting this as say uncovered turning angle. What they find, let it be like smooth way. What was happening, like since I will be having my shock or shock structure, that is what is present here, I will be having my accelerated flow in this trailing edge region. So, that is what is not preferred, because that is what is subjected to say more losses. So, in order to decelerate that flow, this uncovered turning angle, that is what is being provided. Now, talking in terms of say trailing edge thickness. Now, if you look at carefully, suppose say when I am talking in terms of say this blade. So, this is what is my nozzle, I am having this trailing edge, it is sharp trailing edge. When I am talking in terms of say my LP turbine, I will be having slightly blunt trailing edge. Okay. So, the thing is when we are talking in terms of say manufacturing, that time it may be difficult to have this kind of like very sharp edge, that is what is possible. So, in order to avoid that kind of confusion, that is what they have done. That is one of the criteria. Now, let us try to understand what exactly is happening here. Suppose say when I am talking in terms of leading edge, I will be having one flow, that is what is coming out from my suction surface, my other flow, that is what is coming out from say my pressure surface. Now, they are merging together, and that is what, because of presence of my blunt surface, that is what is generating my wake. We have seen in the morning, that is what is my negative wake. Okay. So, if we will be talking in terms, suppose say this, if we will be having sharper edge, then what we talk in terms of formation of vertice. So, here we can say one vertice that will be coming out from my suction side, second will be coming out from say by pressure side, and they combine together, that is what is generating carbon street even. Okay. So, the design for this trailing edge is also of equally important. Now, in order to accommodate that, as we discussed in the morning, for say axial flow compressor, we were discussing about say deviation angle. What is observed? What we have observed is like say we are having adverse pressure gradient, that is what is working. So, you will be having steep boundary layer that will be built up, and often it will be giving me prematured flow. Now, when we are talking in terms of turbine, what is happening? We are having favorable pressure gradient. So, most of the time my flow that will be sticking with my blade only. Okay. When it is working under off design condition, that means with change of incidence angle, then you will be having the formation of your wake. Okay. So, there your deviation angle, that is what is playing role. So, in order to understand, in order to calculate, they have defined one of the parameter, that is what they are saying say f parameter. Okay. That f parameter, that is what is been calculated based on my exit angle, pitch, trailing edge thickness. Here if you look at, this is what is trailing edge thickness, this is what is my momentum thickness coming out from suction side, my momentum thickness that will be coming out from the pressure side. And based on that, the physically they will be putting say the trailing edge, the shape of the trailing edge that will be decided with. Now, let us try to understand here in this case. Suppose say this is what is my representation. Now, here if you look at, I will be having that shock that will be placed here, and that is what is moving on my suction surface. So, if we look at here, this is what is my shock, that is what is starting from my trailing edge, it is moving towards my say suction surface. From here it will get reflected. Okay. And you will be having my expansion waves. Here if you look at, I will be having say expansion waves, and in this particular region we will be having say mixing of two different supersonic say jet, that is what is coming out, and then after later on we will be having reattachment shock, that is what is forming. So, downstream side for the next surface. So, if you look at here, this is what is the movement of my shock towards say suction surface. So, if we consider downstream side for the blade, I will be having different structure. So, the wake, that is what is coming out from my say transonic rotor or maybe transonic stator, that may be subsonic or supersonic, that will be having turbulence flow, that will be having unsteadiness in the flow. So, this is what will be discussed in detail. We will see the video, that is what is representing. This is what is making my flow physics very complex in compare when we are talking in terms of say compressor. So, what it says, if I will be having my exit Mach number to be larger, then my total losses that will be increasing. Okay. Similarly, here this is one of the work, that is what has been reported by Martinelli. What they have observed, suppose say if we will be having say my nozzle, that is what is operating at very high pressure ratio, then we need to design our rotor that need to accommodate very high Mach number, and this is what is reducing my total losses. So, my exit flow angle, as we have discussed, that is what is been decided based on what is my area O, or what we say as a throat. So, based on lot of experimentation, people they have defined for say Mach number of 0.5, the way of calculating my exit flow angle is this. If we are talking, we are having say sonic condition, this is what is my flow angle consideration, and if I will be having my flow in the range of 0.5 to 1, this is the way we need to calculate. Here this is nothing but in terms we say throat Mach number. Now, as we have discussed, one more parameter, that is what is controlling the mass flow rate in the case of compressor. Similarly, here also we are having say stagger angle or blade setting angle. So, if you look at here, say this is what is represented in terms of my axial chord versus my say actual chord. Okay. So, based on the experimentation, people they have defined say when you are having particular blade angle in combination, you can select that as a stagger angle. So, if you look at here, this is what is say initial high say low aspect ratio HP blade, and that is what has been modified in terms of say design by changing the stagger angle. Now, if we are talking in terms of staggering angle, say this is what we say, by changing my stagger angle, what we are doing, we are adjusting our upstream flow. Here my incidence, it was say minus 20, now here I will be having my incidence at 0. Okay. So, the effect of this stagger angle, that is what is reported in the open literature. If you consider, this is what is the change of my say 25, 35, stagger angle minus 30, minus 40, and if you look at here my loading, that is what is changing. Here if you look at, this is what is representing my loading. So, with change of my stagger angle, my CP distribution along my blade, that is what is changing. Now, next criteria what we say is in terms of say blade count. As we have discussed for the compressor, there is no superficial rule for the selection of number of blade. Okay. So, people they are selecting say even number of blade, prime number of blade. Similarly, if we are talking in terms of say number of blades to be selected for say turbine, then there is a criteria, that is what is been proposed by Zweifel. He says like my loading coefficient that will be in the range of 0.8. So, at the mid section you are selecting your Zweifel's criteria as 0.8, and based on that you are calculating number of blade. Let me share you this Zweifel's criteria, that is what was proposed in 1945. As on today also people they are following this. Next what we are talking is in terms of after design the stacking of my blade. Okay. Say I am having number of aerofoils. So, there are two different possibilities for the stacking. If we are talking in terms of rotor, my all blades they are being stacked by CG, and that is how I will be having twisted blade. Okay. Similarly, if I am talking in sense, say I need to have constant nozzle angle, that is what is coming out. So, what we need to do is we need to calculate the mid section of the exit passage, and based on that we need to stack. So, if you look at this is what is the stack about say nozzle angle or stator vane angle. This is what has been stacked about say your CG. Mostly for rotor people they are preferring say the stacking about say at CG. Okay. Now, in terms of blade loading, that is what is mainly been depend on two parameter. One, that is what we say as blade spacing, and second, that is what is say my flow turning. Now, suppose if we are talking in terms, I am having say closely spaced blades. What it means? I will be having more number of blades. So, per blade load that will be lower. If that is what is your case, more the number of blade you will be having larger weight. Larger will be the number of surfaces, that is what is subjected to flow. That means that will increase my friction losses. Okay. Now, suppose say if I am talking in terms of say larger spacing, what will happen? My number of blades will be lower. My larger force per blade, okay, it will be having say smaller weight. It will reduce the friction losses if we are having say fewer surfaces. Okay. So, now the situation is very soon when we will be discussing about the flow 3-dimensionality, that time I will be talking in terms of say selection of number of blade. That is what is playing important role when we are talking in terms of flow unsteadiness. Okay. Let us try to understand the flow passage design. You will be having say different configuration, that is what is possible. One of the configuration is say constant tip diameter flow track, you will be having say constant hub diameter track. Suppose say if I am talking in terms of say constant tip diameter track, then I will be having my rotational speed to be larger because my diameter is more. So, more amount of work I can extract. Suppose if I am talking in terms of say constant hub diameter, I will be having work to be slightly lower. So, more work that can be extracted, what it means, I will be having limited divergence available between tip and the hub diameter. Okay. Now, if I am talking in terms of say high bypass ratio engine, what is happening? For that the flow divergence is significantly and you will be having larger number of stages. Let us try to understand. This is what is a section about what we were talking of. Here in this region, if you look at what is our observation, say I will be having my rotational speed to be high, because what I want to have more amount of work to be extracted, and that is the reason why people they are defining this or they are selecting it as say constant mean diameter design or constant tip diameter design. Okay. When I am talking in terms of LP stages, we are having constraint here, because my aircraft manufacturer he will say you are not having this much space or you need to accommodate your engine, full engine in terms say compressor, combustor and turbine within this particular space. That means this is what is my constraint. Okay. If this is what is your case, if you look at here, I will be having say increasing mean diameter, and this is what is been designed with nearly constant hub diameter. Now, let me share here the interesting observation. What is happening? My flow in the passage, which passage? Rotor and stator passage, I will be having my accelerating flow, and here my flow track, that is what is diverging passage. Okay. So, you are having say diverging passage with accelerating flow, that is what is giving all three dimensionality to your flow in this region. Suppose say when we are talking in terms of say military engine, say this is what is say my HP and LP configuration, mostly they are preferring say constant mean diameter. Okay. And they are having passage, special passage in sense they are having convergent divergent passage. Okay. So, let us have tea break now, then we will be starting with the flow three dimensionality, and then after we will discuss something in terms of say unsteady flow, what we are observing for HP as well as LP. Fine. Thank you. Shall we start? Yeah. So, now let us talk in terms of losses, that is what is happening in the blade passage. This is just idea in that sense, we will be discussing all this in detail. What we say, we will be having losses, they are being classified as say profile loss, annulus loss, secondary flow loss and tip clearance loss, they are the major contributors. Now, when we are talking in terms of say profile loss, that is what is because of my growth of boundary layer on the blade surface. So, here if you look at this is what is my blade, on that we will be having say growth of boundary layer because of my solid surface. Okay. And when my flow that will be coming out because of this bluntness what we have discussed, it will be having negative jet. Okay. The size of or maybe the wake that will be coming out at the exit from the trailing edge, that is what is depending on my flow, that is what is entering or say incident on my leading edge. So, when we are having incidence angle that to be changed, accordingly my wake size what we say or the profile loss what we say that will be changing. Next, that is what we say in terms of say annulus loss. That annulus loss, that is what is and in the inner surface at the outer surface of my annulus, that is what we need to consider. We say near the hub, near the tip region. Secondary flow losses, this is what we will be discussing in detail, and tip clearance loss, that is what is having mechanism different than that of what we have discussed for axial flow compressor. So, let us try to understand in detail. Say this is what is say turbine cascade. So, if you look at here, this is what is being placed in a linear way. So, it is a linear cascade. Now, what is happening, suppose say at say 50% of my span, this is what is my visualization or the streamlines what we have plotted. So, if you consider here what is happening, my flow that will be incident at some angle. So, I will be having stagnation point that will be placed somewhere here, and from that stagnation point I will be having my flow that will be moving towards say my pressure surface, and it is moving towards my suction surface. Now, because of my shape of this section or the passage, what is happening, my streamlines, that is what is getting converged, or maybe if we look at here, that is what is giving me acceleration in other sense. Okay. Now, if we plot the CP distribution, then this is what is representing my CP distribution. Okay. So, if I am talking in terms of my span say near the hub or near the tip region, I will be having say end wall, what they say at the mid section I will be having maximum value of the CP or say higher work done. Near my end wall I will be having my CP distribution to be lower. This is what is common, what we have observed even for our axial flow compressor. Now, let us try to understand what exactly is happening near my wall. So, if we consider near the wall, what is happening, we are having say solid surface, that is what is having the growth of boundary layer in that direction. Now, with that solid boundary layer or say boundary layer presence, what is happening, we will be having say differential pressure on pressure side and suction side. So, I will be having the variation of pressure. So, what it will do, it will deflect my flow, it will try to deflect my flow. Before going into detail, if we consider here, like I will be having one point, that is what is known as saddle point, that is what is representing, is acting like a separation line about which my flow is getting deflected. So, if we look at in the sense, so here this is what is my saddle point and my flow, that is what is moving in this direction. So, I will be having separation line, that is what is coming here, I will be having one separation line, that is what is moving on my suction side, I will be having one separation line, that is what is moving on my pressure side. Okay. Now, this deflection of my flow, if you look at this line is moving more towards my suction side. The reason is what is happening, we will be having the differential pressure, and that is the reason why my flow is trying to move more towards in that region. Now, in this particular region, this is what is like if we consider say pillar. So, say in river when we are having say pillar, what is happening in that particular region, this kind of structure what we have observed. So, similar kind of structure we are observing here when my flow it is getting obstructed with say this circular shape. Okay. So, now here in this case it will be splitted into two, that is what people they are defining as say shoe vortex or horseshoe vortex, it is having that shape. Let us try to understand here, this is what we mean to say. Now, here in this particular region what we say, like I will be having the horseshoe vortex, that what will be forming. Okay. Now, in detail if we try to understand, this is what is my flow, that is what is entering inside. Okay. Now, on my pressure side what is happening, my flow or that will try to move towards my suction side. So, this is what is moving towards the suction side. Similarly, other leg what we say on suction side, that will try to move on towards my suction surface. So, this is what is moving on the suction surface. So, if we look at here at section AA, if we will be putting, that is what is showing me two vertices. Okay. Now, near the point BB, if you look at carefully, from here I will be having sudden change of my curvature. So, from there I will be having new vertex, that is what is forming here. Okay. That's what is known as a corner vortice. That's what is happening from the suction surface. Similarly, one more vortice that will be forming from here, that's what is known as a pressure corner vortice. Okay. Now, if we look at in overall sense, then we will be having say the wall vortex that will be induced because of my passage. What you mean by that passage? Just try to understand in the morning what we have discussed. What is happening? We are having our solid body. That solid body, that's what is having the growth of boundary layer, and on the both the surface we are having say differential pressure, and that differential pressure that will be forming my new vortice here. So all together if you look at here, they will combinely that's what is forming one big vortice. That vortice we are defining as the secondary flow. Okay. So the thing is, we are having boundary layer growth along with my pressure gradient near the end wall. That's what is creating this kind of flow structure. The thing is, my secondary flow, what we have discussed near the end wall, that's what is being influenced by my incidence angle. It may possible you will not be having say corner vortex to be formed. It depends on my geometry. It depends on my flow turning angle. It is depending on my solidity. What we mean by solidity, that's what is my say core to pitch ratio. It depends on my aspect ratio. Suppose I will be having say smaller blade when we are talking in terms of HP. What is happening? My span, that's what is very low. Under that condition, the chances for the formation of this secondary flow, they are more. Then we will be having blade loading distribution. That is also playing the role. That's what is defined in terms of my curvature of the blade and inlet vortex intensity. This inlet vortex intensity, that's what is defining in terms of what is there upstream. Okay. Now, in order to minimize this secondary flow, lot of research and development activity, that's what is going on. People, they have preferred say skewed and swept kind of blading. Then they have done the modification in the leading edge. Suppose if I am talking in terms of this leading edge, rather you need to avoid the formation of the horseshoe vortex in that region. For that they are putting special kind of shape near the leading edge. Non-axisymmetric end wall profiling, that's what I am saying. Now, here if you look at in overall sense, this is what is a picture. Very interesting case, that's what is happening when we are talking in terms of say your HP turbine or HP nozzle. Here this is what is representing my structure, shock structure. So this is what is the wake, that's what is coming out from my trailing edge. Here somewhere I will be having my shock, that's what is present. What it will do, here in this particular region we will be having adverse pressure gradient. So we will be having the formation of say separated flow. Now on the downside, you just try to understand what is the complexity. We have shock, we have boundary layer, then after we have the combination of shock and boundary layer, and that's what is moving downside. Now that downside, it will incident, suppose say if I am considering this is what is say my rotor consideration, then this is what is rotating. So my whole flow structure, if you look at here, this is what is moving inside my passage. Okay. So it is nicely been explained. We will see what exactly and how exactly we need to understand. Suppose if I am talking in terms of say tip clearance, here similar is the scenario what we have. What it says, smaller will be your tip clearance, you will be having say loss to be reduced. But here if you look at carefully, what is happening, my rotation is from suction surface towards the pressure surface. That's what is my blade rotation. What is happening near the tip? My flow that will be moving from pressure side to the suction side. Okay, that's what is a reverse kind of situation. So here that's what is generating separation bubble, and in this region particularly you will be having jet kind of flow. So here this is what is my thick blade. Okay. Or you can say when I am cutting my blade at particular section, suppose a maximum thickness section, this kind of structure I will be observing. Suppose say if I am moving towards the downside, that will be thinner blade. So, now what is happening? Now, my flow that will be coming out here, that will be getting mixed. So, this is what is particular region where I am having growth of boundary layer, one flow that is what is crossing, and whole mixing that is what is occurring, and that is what is generating one vortex. That vortex that will try to move in downside. Now, my incoming flow is coming from one side, I am having my tip leakage vortex, they combinedly together, and that is what is try to move more towards my suction surface. Okay. So, this is what is my tendency. Now, what is happening now, in order to have this occurrence of this vortex, people they are preferring different kind of end wall shapes. Suppose if you consider, they have kept the rim on the suction surface, they have kept the cavity in this region. So, in detail they are studying the 3D modeling for these tip shapes. Okay. Let us move towards my LP turbine side. So, this is what is a blade, that is what is my LP turbine blade. If you look at, this is what is the flow visualization what they have observed. What is the observation? If you look at here, I am having my secondary flow, you can easily observe here on my suction surface. Okay. Similarly, I will be having my secondary flow, that is what is happening near my hub region, near the hub, say on my suction surface. What is the reason? Now, you can understand I am having two vortices, they are coming out. Okay. That is what we have defined as my secondary flow. Suppose say I am having say small aspect ratio blade or say HP blade, what will happen? I will be having merging of these two secondary flows and it will give you one vortex. Okay. Now, here if you look at, there is one thin line what they say, that is what is boundary layer separation. Okay. And this is what is my trailing edge. Now, the thing is, when we are talking in terms of say design, you have designed everything so nicely, your engine is working fine on the ground. But when you are putting that at cruise condition, what is happening? All the way your mass flow rate, that is what is changing with your density. So, it is, if you look at carefully, this is what is representing under cruise condition the variation of my Reynolds number. So, if you look at here, my Reynolds number particularly in LP section, that is what is lower. Okay. So, what will happen? My flow physics what we are talking in terms of my suction surface, that is not as per what we have designed for. Okay. And that is the reason here, if you look at, we will be having say the boundary layer that will be formed and you will be having my flow separation, that is what is occurring. And this is what is tend to be in terms of losses. If you consider here, if this is what is my separation, you can understand I will be having my profile loss to be large. Okay. And that in terms decreasing my performance, so it will not generate the power what we are expecting. Okay. So, the thing is, now when we are talking in terms of say different profiles for the turbine, we need to have this turbine profile, that is what is mainly been depend on my Mach number, stress level and various other parameters. So, if we talk in terms of strictly speaking, there are few profiles they are available online or available in open literature, that is what is been in terms of say NACA profile and Agard profile. Basically, that is what is with say circular arc or parabolic arc. Because of proprietary nature of their work, industries they are not putting the profiles, plate profiles, especially turbine blade profile or compressor blade profile in open literature. So, you need to start, suppose say if you say sir I am starting with the design of my turbine, then you need to select the available data. Based on that, you need to custom tailor. That means you need to modify it based on your CFD study. You can do your numerical study, try to understand what is happening on my suction surface, what is happening on my pressure surface. Based on that physics understanding, you modify your profile, maybe you need to change the thickness of your aerofoil, maybe you need to change the maximum camber of your aerofoil, maybe you need to change the maximum thickness of your aerofoil, maybe you need to change the leading edge shape, maybe you need to change the trailing edge shape. Okay. So, this is what is available in open literature, say NACA profile, that is what is A3K7 and B1E1I1. So, if you look at carefully in terms of this comparison, what is happening, my maximum thickness placement, that is what is at a different location. This is what is representing in terms of my cambered angle, say 65, 80, when I am increasing my maximum thickness and cambered angle, you will be having some kind of blade, that is what you say impulse turbine blade. Okay. So, this is what is mostly been used in terms of research, that is what is known as 106 aerofoil or T106 aerofoil. For that open data, that is what is available. So, people initially when they are starting their design, mostly they are selecting this as a profile and later on as per the requirement they are modifying. If you look at here, these are 4 different configuration. Here in this case, I am having my inlet as subsonic, my outlet as supersonic. Here in this case, I am not having any kind of shock to be present. This is what is a tip profile, that is what was being used for say steam turbine consideration, in which my inlet is supersonic, my outlet is supersonic. And this is what is a profile, that is what is representing supersonic flow at the inlet and supersonic flow at the outlet, and it is nearly in terms of impulse kind. Now, here if you look at, these are also the turbine aerofoils, just try to understand. Okay. So, this is what is say for E3 engine bleeding, this is for say nozzle or vane, and this profile is for blade. Okay. So, if you look at here, that is what is having some different kind of leading edge shape, and that is what is giving me my variation of pressure on pressure surface as well as on my suction surface. Now, you can understand how nicely they are managing their flow near the leading edge. Okay. Similarly, here if you look at, this is what is the rotor blade. Okay. And in rotor blade, if you consider, I know I will be having my acceleration of flow in that region. So, this is what is the acceleration of flow, and then after it will remains constant, almost constant. Okay. Now, what is happening? If I look at on my suction surface, I will be having my acceleration of flow, and then after I will be having say this is what we say in terms of my flow moving downside. Somewhere here, suppose say I am putting second aerofoil here. So, somewhere here in this region nearly 60% it will be having shock, and that shock what it will do? It will give you rise of pressure. So, this is what is giving me rise of pressure, and again that is what is moving downside and merging. So, this is what is being used for say advanced turboform design. So, if you look at these profiles, it looks like some odd shape, but you know you are having the constraint with the size, overall size of the engine. You need to do more amount of work with limited size. Under that condition, you will be having your profile like this, stator profile and rotor profile. Similarly, here stator and rotor profile, and this is how my CP distribution will be. Now, these days people they are talking in terms of having special designs, in which what they are doing, they are initially defining the CP distribution, and based on that they are designing their profile. Up till now what people they were doing, they are doing their experimentation on cascade, based on that they were finding their CP distribution. Then later on people they started using numerical tools, based on that they are calculating their CP distribution, and then after they are changing. In place of that, dedicatedly they are defining this pressure distribution, and based on that pressure distribution they are doing inverse problem. That means based on this CP distribution what need to be my profile. That is what is known as inverse design. So, if we compare in terms of pressure distribution for typical compressor, we will be having say various differences Okay. So, pressure drop what we are talking in terms of turbine, that is what is higher compared to your pressure rise what you are expecting in compressor. Your blade turning angle that will be in the range of say 20 to 45. Correspondingly, my blade turning angle for say turbine that will be in the range of as high as 160. Okay. So, design of my pressure surface for both the cases, it is usually been designed for constant Mach number or constant pressure. So, not much work, that in sense people they are talking for say pressure surface. Okay. Now, in the case of say compressor, my suction surface it will get accelerated initially and then after it is getting decelerated. Okay. And the separation criteria that will prevent the rapid deceleration. If we are talking in terms of say turbine, cruelly speaking, it says you will be having acceleration throughout from the leading edge to say trailing edge. Okay. Now, when we are talking in terms of say turbine, then usually designers they are preferring like formation of shock that they are acting like it is a loss. Okay. And for this reason, my inlet that is what is say subsonic, exit supersonic, that is what is not uncommon, that is what is commonly been observed for aircraft engines. So, when we are talking in terms of say compressor, what we are using, we would like to have shock to be placed, because we need to take the benefit of the shock formation, and that is the reason why. So, my shock what we are observing, we want that shock to be placed inside the passage. In case of turbine, we would like to have our shock to be placed not within the passage. Okay. So, the acceleration near the pressure surface is much more pronounced towards the trailing edge. So, let us see. Suppose say this is what is my say arrangement for the blade. Now, this is what is working under three different conditions. One, it says my inlet and exit they both are subsonic. Okay. And it is having say supersonic flow in this region. So, what will happen, suppose say my exit what we are expecting is in terms of say 0.7 and 0.9. So, this is what is my CP distribution. Next, if we consider my inlet is subsonic and supersonic exit. So, if I am considering say I am having say Mach number 1.2, what will happen here? If you look at this is what is my Mach 0.9 at the exit. Now, when I am saying I am having say my Mach number 1.2, I will be having my shock to be placed here. So, what that shock will do? It will give the rise of pressure. So, if you look at here, this is what is my rise of pressure, and then after again it will be accelerating. Similarly, if I am talking in terms of 1.4, so this is what is my situation. Okay. So, the thing is you will be having initially your deceleration of flow and then after you are having say acceleration of flow again. So, the thing is the exit region what we are talking, that is what is of very much importance when we are talking in terms of turbine. When we are talking in terms of compressor, this passage what we are talking, that is what is very important. So, let us try to understand in terms, suppose say conventionally when designer is doing design, he always care for that no shock that will be formed at the trailing edge. Okay. So, this is what is the situation. It says like I need to have my design such a way that my exit pressure and design pressure they will be same. So, this is what is my velocity triangle for that, in which my beta 2 is constant. Now, what is happening? Suppose say if I am talking in terms of say application in turbine, suppose I am increasing my rotational speed or decreasing my rotational speed. Increasing and decreasing, that is what is depending on velocity with which my flow that will be coming out from my nozzle. Okay. Suppose if I consider say I will be having increase of velocity. So, under that condition my exit pressure that will be lower than that of my say design pressure. So, you can understand that is what is acting like over expanded nozzle. So, here if you look at from this trailing edge, I will be having my expansion fans that will be terminated by my normal shock, okay, and this is what is your flow that will be coming out. So, under that condition, when my rotational speed is higher, and this rotational speed, that is what is changing as per my requirement, because when I am talking, I am having say flight envelope, say I am having takeoff condition, I am having cruise condition, I am having landing condition. Suppose if I am talking in terms of say military aircraft, I need to do lot of maneuvers. So, all this condition, my rotational speed, what we are talking, that will be changing as per my thrust requirement. So, under that condition, my flow physics near the trailing edge, that is what is changing. Now, what is happening? Suppose say if I consider my rotational speed to be lower. So, under that condition, my exit pressure that will be greater than that of my design pressure. If this is what is your situation, you will be having your expansion fans, that is what is placed here, and that is what is getting reflected. Okay. So, the thing is, designer never designed in that sense having say your exit Mach number to be in the range of say sonic or the say transonic or supersonic. It depends. It depends. Suppose say if I am expecting more amount of work to be done, what it means, I need to have higher velocity. When I am talking in terms of say HP turbine with limited number of stages, then they are forced to do this kind of design. You cannot say I want this to be shock free operation. Okay. For that purpose, they need to modify this profile accordingly. So, morning what we have discussed, very complex flow dynamics what we are observing in the turbomachinery, that is what is because of your secondary flow. That secondary flow, that is what is because of viscosity and complex geometry. That is what has been nominated by say your passage flow, leakage flow, corner flow, trading flow, horseshoe vortice, scraping vortice. This all together, that is what is giving the three dimensionality to your flow. Inherent unsteadiness is due to the relative position between rotor and stator. Slowly we will be moving towards that condition. Now, the flow pattern near the wall region, if we look at, we will be having say laminar flow, what we have seen, maybe having say transition flow, maybe having turbulent flow. Okay. Now, if we look at on the turbine blade, what you prefer? You need to have turbulent flow to be placed on the surface, suction surface, or laminar flow to be placed on the suction surface. What is your preference? You want your flow to be turbulent flow. Okay. Now, your flow may be incompressible, it may be subsonic, it may be transonic, it may be supersonic. Then you will be having strong interaction with the solid body. Now, when we are talking in terms of turbine, then again we have complexity, that is what is because of hot section. Now, in order to have that hot section to be handled, you need to have cooling mechanism. So, along with all this complexity, now you say, sir, please accommodate the cooling facility. So, all my flow physics what we are talking, that will become very complex. That is what is a very challenging part. So, the flow in the turbine is highly unsteady because of periodically encounter flow distortion, that is what is generated by upstream and downstream blades. We will see what exactly. So, it is this unsteadiness that has important consequences on your efficiency, your blade loading, mechanical fatigue, flutter, heat transfer issue, thermal fatigue, noise generation, so many parameters. What Zhu has done, he has defined say unsteadiness in two ways. What he says, the instability in the flow field, that is what is because of say rotating stall, surge, flutter, flow distortion, etc. That is what we can avoid when you are doing your design. We can take care of. The second category of unsteadiness, that is what is say inherent unsteadiness, or that is what is because of relative motion between rotor and stator in the case of say multi-stage configuration. Here if you look at Lagraft, he has defined in terms of length scale as well as in terms of frequency, and this all what we say is nothing but it is a unsteadiness. That is what is creating unsteadiness in my flow. What are they? You will be having transient operation, okay. You will be having surge, rotating stall, clocking and hot streak migration. We will see what exactly is this. You will be having flutter, that is what is having very large scale. You will be having say cooling, that is what is having say small region. Wake interaction, if you look at, that is what is covering very wide area. Trailing edge vortices and inflow turbulence. Okay. So, now if we consider, then we need to understand the physical mechanism for the unsteadiness. That is what is because of potential interaction. Now, what is that potential interaction? What is happening? We are having the gap between your stator and rotor. That particular region, that is what has been defined as potential flow field. Okay. So, my Mach number and axial gap between this rotor and stator, that will decide my potential interaction. Okay. Next, that is what we are defining as a wake. What is that wake? That is what is moving towards the downward direction. The wake profile, that is what is nothing but it is a variation of your velocity deficit. It can be influenced your surface pressure, it can influence your surface heat transfer, it can influence your boundary layer behavior on the surface. What we are talking in terms of change of incidence angle. Okay. Then you will be having shock wave interaction when it is operating under the transonic region, that is what is generating my unsteadiness in the flow. We will see. Next, that is what we are defining in terms of say streamwise vorticity. That is what we have defined specifically when we are having say low aspect ratio blade, this situation, that is what is occurring. Next, that is what is defined as a hot streak. It is nothing but what is happening, my flow that will be coming out from my combustor, it will be having say variation both in circumferential direction as well as in the radial direction. So, because of this variation in my temperature profile, that is what is giving my unsteadiness in the flow. That is what is defined as a hot streak. So, let us try to understand my unsteadiness in my LP turbine. What is happening? For my LP turbine, profile loss, that is what is one of the major contribution or major contributor. What is the reason? Because we are having high aspect ratio blade and you will be having growth of boundary layer. If you look at what we have discussed is in terms of say cruise condition and operation of my Reynolds number. So, you will be having major contribution because of that. Now, flow, that is what is inherently unsteady, that will be caused by the relative motion between your adjacent blade row. The two primary form, that is what is wake, that is what is coming out from upstream blade and potential flow blade between upstream and downstream, and the interaction of this potential flow with the wake region. We will see in detail. Research indicate that very small change in the static pressure flow field may subject it to boundary layer and that will give the separation or the separated flow on the rear side of my suction blade. That is what we have observed. Now, let us try to understand the wake transport mechanism. Okay. Now, here this wake transport mechanism, that is what is been studied by different researchers, say Smith, Stringer, Hudson. They have defined this mechanism as say bowing, reorientation, elongation and stretching. Now, here if you look at, this is what is the analysis, that is what is the data from experimentation and as well as from my computational study. What they say is at different time scale you will be having the movement of the flow. What is happening? The wake of the bowing is a wake fluid originating, that is what is from my leading edge in this plane. Okay. It will be moving with higher velocity near the suction surface and it is moving with a lower velocity. So, it is having bow kind of shape. Now, what is happening? The reorientation that will be occurring because my velocity here near the suction surface, that will be larger. So, what it will do? it will give the momentum to this fluid that will try to move in downward direction. This is nothing but turbulence kinetic energy, they have represented in terms of say velocity. Now, difference in the convection velocity that will cause the wake to get elongated. So, if you look at here, this is what is getting elongated. So, that is what is known as elongation. That will turn to decrease the wake width to conserve the vorticity of the working fluid. Now, stretching, that is what is occur at the first part of my wake, that is what is reaching to leading edge. So, again you will be having say entering of this wake. So, just try to understand, suppose say if I am talking of upstream, I will be having my wake, that is what is coming out, that wake, that is what is moving inside my passage, and then after it will be having say different formation, and that is what is coming out. So, this is what is been nicely defined by Binder. So, here if you look at this is what is say rotor 3 and I am having stator 4. Both the cases what is happening, I will be having number of blade to be different. Okay. Now, what was happening, say my flow, that is what is coming out from my rotor blade, that is what is having some wake. That wake, that is what is entering inside the passage, what we have discussed in terms of wake transportation. Now, that will be coming out from my trailing edge, this is what is coming out from my trailing edge. Now, what it will do? It will move inside the passage. This is what is a region, that is what is known as potential flow field. Okay. Now, my wake, that is what is coming out from the stator, it is moving in this direction. At the same time, what wake, that is what was coming out from my rotor, earlier rotor part, that is moving in other direction. Okay. So, now here under this condition, this is what is at some section, say mid section. What is happening? We have all kind of flow 3 dimensionality. Suppose if I am observing that near the hub region and near the tip region, suppose a tip region, what we have? We are having tip clearance flow. Now, that tip clearance flow, that is what is merging here. Suppose if I am talking in terms of say near the hub, I will be having horseshoe vertices, that is what is creating my 3 dimensionality flow. So, all together that is what is giving very complex flow field. Okay. Now, wake boundary layer interaction, as I told what it is doing, this is what is striking on my say stator blade. Okay. This wake, that is what is. So, locally what it will do, it will give you the acceleration of flow in this particular region, say this is what is my acceleration of flow. Locally I will be having shock to be formed in that region. So, this shock what it will be doing, now it will generate my boundary layer, because I will be having pressure gradient, differential pressure, okay. And that is what is forming my boundary layer. That boundary layer, that is what is moving in downward direction. So, suppose if I consider here, somewhere here I will be having that transition to be occurred. Okay. At that transition, that will be changing the size of my stator wake. Okay. So, now let us try to understand what is happening in the case of say our HP turbine. What is happening? Our interest is to have low aspect ratio blade. We want that to be intentionally. Okay. Suppose say if I will be having say this is what is the failure of my blade, my HP vane. What is happening? Say we will be having our end flow, end wall flow, it says it is inversely proportional to my aspect ratio. So, if I will be having lower aspect ratio, I will be having more end wall losses. Okay. And in this region what is happening, we will be having say inherent unsteadiness, that is what is because of end wall region, and there is an interaction of my secondary flow and tip vortex flow and periodic wake, potential flow field, all together that is what is creating a lot of trouble in terms of flow field. That is what is giving the unsteadiness of my flow. Okay. So, this is what we have discussed earlier in terms of formation of my shock. It depends on what is the kind of design I am having, what is the kind of trailing edge I am having. Now here if you look at, this is what is representing what we were discussing in terms of shock. This shock, that is what is getting reflected here. As I told, it will be striking on my suction surface. Here I will be having say my shock boundary layer interaction, and that is what is generating my flow separation in that region. Here locally if you look at the exit, I will be having shock structure, that is what is forming in this direction. So what it will do, maybe one of the shock that will be striking on my suction surface, that will what will be acting like a normal shock. You will be having my separation of flow, that will be happen. This is what is say coolant injection and rim seal flow interaction. We know for HP turbine, my flow that will be entering at very high temperature. Now if we will not allow it to cool, it will get melt. So in order to provide that cooling, we will be extracting the air from HP compressor, and that is what is flowing through my rim seals, and that is what is entering inside these holes. Now my flow that will be coming out from this hole. So we are already having typically 3-dimensional flow because of all your hodgepodge. Additionally, when my flow, that is what is coming out from my say stator or rotor blade, what will happen? It is creating additional complexity in the flow, or it will provide additional unsteadiness to the flow. Very little literature, that is what is available in open literature. Okay. So the companies or engine manufacturing companies, they are having their own research and development activity. Because of their proprietary nature, they are not putting that in open domain, because engines are flying. So the thing is, they must have done something in that sense, but it is not for open domain. This is what we say in terms of hot streak. What we have discussed. So if you look at here, this is what is my nozzle vane and this is what is my rotor. Okay. So what is happening? We are having the variation of my temperature both in circumferential direction as well as in my radial direction. So what it will do? It will be impinging locally in particular region. So in that region locally my temperature will be rising. If that is what is your case, what will happen? You will be having the melting of that particular blade section. Okay. Now in order to avoid this situation, people they are talking in terms of say clocking. Clocking is nothing. What you need to do is you need to manage your hot streak. Okay. How you exactly you are doing, that is what is based on my selection of number of blade. Okay. So maybe Professor Watanabe, he will be discussing more in terms of this clocking effect when he will be touching this aspect. Now this is what is why this video is not coming. Say this is what is one of the 3D analysis, unsteady analysis, that is what has been reported by TU Grace. Okay. Here this is what is their PIV image, this is what is showing me the gradient. If you look at, just have a look at carefully, this is what is their PIV and LDV data. Okay. This is what is showing my gradient. If you just try to understand what is happening, this is what we were discussing in sense. Okay. So this is what is my rotor, that is what is moving downside. Here this is what is we are having say stator, that is what is having say two different colors, and we will be having say carbon vortex streets, that is what is happening. That is what is striking here, that is what is moving down in this direction. Again you will be having the variation. So if you look at, that is what is having the waviness in that sense. This is what is representing the losses in terms of entropy. So, main losses, that is what is happening near my tip region. Okay. So, this shows my entropy level, that is nothing but in terms of losses you can understand. Okay. So, in between what we say potential flow region, this is what is happening in terms of the formation of my wicks, okay, or the secondary flow, that is what is changing its nature. Okay. So, this is what is entropy contour, you can say this is how my flow is moving. Okay. Now, in overall sense, what we are discussing, the aerodynamic source for the unsteadiness in the turbine, that is what is been classified in two ways, saying periodic and non-deterministic. What we say in terms of periodic is my potential interaction, that is what is related with my velocity and pressure field of adjacent blades. That is what has been affected by my axial gap and the Mach number. Okay. Next, that is what is say vertical or entropy wake, that is what is large structure flow structures will be having shaded wakes. Shock boundary layer interaction or shock wave interaction, that is what is say extended from upstream towards the downstream direction, and that is what is giving you unsteadiness in the flow. Hot streak, what we have discussed, that is nothing but it is non-uniform distribution of my temperature, okay, with the flow that is coming out from the combustor. That is also creating the trouble in terms of my first stage rotor, okay, especially on my suction surface. In terms of non-deterministic, you can understand we will be having say mixing flow, that is nothing but tip leakage flow, shroud leakage flow, coolant injection, shear layer, what we say in terms of wake, secondary vertices. One more thing, that is what we are not touching, is in terms of say turbulence. My free stream turbulence, boundary layer interaction near the end wall and the suction surface, that is what is creating all kind of unsteadiness in my flow. Especially if you look at here in terms of say aerodynamics and unsteady aerodynamics, the feature in terms of turbine is much more complex. Okay, because my shock structure, that is what is happening near the trailing edge, and the way in which my flow is behaving between rotor and stator based on my number of blades and number of vanes, the whole physics, that is what is changing. And this is what we have discussed in that sense. This is what is the challenging part, what we have discussed. Suppose say this is what is with your volcano S. You are already having your complex flow, you need to have cooling, and because of this S particle, that is what is getting deposited, your all holes they are getting blocked, because those holes are micro holes. Now the situation is immediately your turbine that will get melt, or turbine rotor, turbine vane, that is what is getting melt. Okay. So, in overall, if you look at here, now rather saying collared triangle or Collar's triangle, we can say that is what is now it is tetrahedron, because the aspect of thermal force also we need to consider for. So, when we are talking in terms of say overall performance of the turbine, suppose say this is what is representing in terms of say mass flow rate versus my expansion ratio and efficiency. If you look at over the range, my efficiency with different speed lines, my efficiency, that is what is remains constant. What is the reason? The reason is my flow is the favorable pressure gradient flow, and that is what is permitting my efficiency to be constant, and that will be in the range of say 90%. Okay. Now, when I am talking in terms of my mass flow rate, this is what is my low mass flow rate region. For that particular speed, you will be changing the mass flow rate. There is a situation that will arise where all my these speed lines that will merge together and you will be having choke flow. That means there is no further increase of mass flow rate, that is what is possible. This is what is the representation in terms of different speed, that is what is represented in a different sense. Now, so in overall if you look at the performance of my turbine, it is limited by the three factors. One, that is what we say is in terms of say compressibility. Second, that is what is in terms of stress. And third, what we say is in terms of my inlet temperature. So, compressibility, that is what is limiting my mass flow rate through the turbine. Stress limit, that is what is putting constraint in terms of rotational speed. And performance, that is what is mainly been depending on my temperature. So, design must be compromised in terms of maximum temperature and maximum rotational speed. What it says, for the given pressure ratio and the efficiency, my turbine work per unit mass is proportional to my inlet stagnation temperature. If you increase 1% turbine inlet temperature, that will be producing 2 to 3% power output you can increase. So, now the thing is, it says you move towards higher turbine inlet temperature side. Now, at the same time when we are discussing, that is what is required very effective cooling for both nozzles and rotor vanes. Okay. Now, here what we are talking in terms of Mach number, the question need to arise in your mind like what Mach number? Mach number we are defining in terms of velocity divided by your sonic velocity or root gamma RT. Suppose if I am talking in terms of temperature, my temperature is higher, then it need to come subsonic flow. But this compressibility what we are talking, that is not been calculated at that condition. You need to calculate at critical condition. So, you need to calculate critical Mach number. Okay. So, that critical Mach number, that is what is representing my Mach number in the case of turbine. And this is what is the end of this lecture. Thank you very much. If you have any doubt, you can ask.